Here's a circle. The genius Leonardo da Vinci attempted to draw the square with the same area. His interest in this challenge might be secretly reflected in this piece. Is it possible to construct that square using only a straight edge and compass? Let's explore the squaring a circle and its proof. There's an inscribed square and a circumscribed square. The area of the circle lies between the areas of the two squares. Somewhere between them is the square we are searching for. To prove this mathematically, we need to turn the problem into an algebraic one. Let's say the circle has a radius of 1. The area of the circle is pi. For a square to have the same area, its side length must be root pi. Now, here's the real question. If we are given a length of 1, can we construct root pi using only a straight edge and compass? This is the algebraic meaning of the problem. If root pi is a constructible number, then the problem can be solved. But if it's not, the challenge remains impossible. So we need to figure out whether root pi is a constructible number or not. This length is 1. Using construction, we can add or subtract this length repeatedly. As a result, we can create natural numbers. Draw an additional line and repeat the unit length. Draw a line connecting these 2 points and draw parallel lines to this line. We can divide this segment into equal parts, creating any desired fraction. We can even construct some irrational numbers, specifically square root of rational numbers. This length is 1. This length is x, which is rational. Add 2 lengths. Draw a perpendicular bisector. This length is divided in half. Draw a circle with a radius of this half length. Draw a line passing through this point. This triangle is a right triangle. These triangles are also right triangles, and they are all similar. If we call this length a, we get the following proportion. A becomes root x. We've constructed root x. If this length were root x, this length will be the square root of root x. By repeating this process, these lengths are also constructible numbers. But the numbers like this still can't be constructed this way. Let's get back to the problem. Is root pi a constructible number? Since it's a square, it would be constructible if pi itself were constructible. To answer this, we need to understand the nature of pi. Humans discovered pi long ago and spent centuries trying to figure out its exact value. However, pi couldn't be expressed as a rational number. Eventually, it was proven that pi is irrational, not rational. That happened in 1761. But here's the catch. From the perspective of constructibility, not all irrational numbers are the same. Some, like square root of 2, are constructible. Others, like cube root of 2, are not. So, just knowing pi is irrational isn't enough. We need to dig deeper. And this is where algebraic numbers and transcendental numbers come into play. Algebraic numbers are roots of polynomial equations with integer or rational coefficients. The number 3 is the root of the equation x minus 3 equals 0. The fraction 3 over 4 is the root of 4x minus 3 equals 0. The square root of 2 satisfies x squared minus 2 equals 0. The imaginary unit I satisfies x squared plus 1 equals 0. The complex number 1 plus I is the root of x squared minus 2x plus 2 equals 0. So, algebraic numbers include integers, fractions, square roots, imaginary numbers, and complex numbers. But not all complex numbers are algebraic. Some numbers are not roots of any polynomial equation with rational coefficients. These are called transcendental numbers, and they are fundamentally different from algebraic numbers, just as irrational numbers differ from rational ones. In 1882, it was finally proven that pi is not algebraic. Pi is one of transcendental numbers. So, what does this proof mean for squaring a circle? Well, constructible numbers include natural numbers, rational numbers, and certain square roots of rational numbers. All of these belong to the category of algebraic numbers. Every constructible number is algebraic, but not every algebraic number is constructible. So, when pi was proven to be transcendental in 1882, it gave us the final answer to the problem. Pi isn't an algebraic number, so it can't be constructible. And if pi itself isn't constructible, root pi can't be constructible. It's impossible to construct a square with the same area as a circle. Finally, let's check how it was proven that pi is a transcendental number. It involved proof by contradiction. Assume that pi were an algebraic number. Then pi would also be algebraic, because multiplying two algebraic numbers still gives an algebraic number. But here's the twist. The Lindemann-Weierstrass theorem states that e to the power of any non-zero algebraic number is always transcendental. So e to the power of pi must be transcendental. But Euler's famous formula says e to the power of pi equals -1. And -1 is clearly an algebraic number. That's a contradiction that resulted from the assumption that pi was algebraic. So the assumption must be wrong. Therefore, pi is transcendental.